Okay, welcome to lecture 4.7. Okay, let me quickly show you okay, what the CDF looks like for a Weibull, for a random variable distributed Weibull. So if UI is distributed Weibull, then probability UI less than or equal to Z equals this, okay? E to the negative E to the negative Z. That's it. Okay, that's kind of complicated actually, but if that's the CDF, then the probability, darn it, I put Z's in as the generic variable. So UI plus the scene utility just gives you that nice form that I described in the last lecture, last segment of session 4, I guess. Way to remember that, you might check that, so this is called the F of Z, usually is capital F as a CDF. You might check. Sometimes I can't remember where the negative signs go. Here's a way to check. We know that negative F of infinity, so that's probability UI is less than infinity. That's got to equal 1. So let's check. That should equal e to the negative, e to the negative infinity. And so e to the negative infinity has got to be 0. So this is 0. So this simplifies to e to the negative 0, which is just e to the 0, which is 1. So it works, okay? F of infinity equals 1. Now we should also get f of negative infinity. We should get that equals 0. So the probability UI is less than negative infinity should be 0. Let's check. We get e to the negative, e to the negative infinity. That equals e to the negative, e to the infinity equals e. This is infinity, e to the negative infinity, which equals 0. Okay, so it works. Okay, well, at least it checks that these two values work, that it really is a proper CDF. Okay, so that is the CDF of Weibull. Yeah, I would say I've actually asked that on a test before. I do want you to know that. That's what the CDF of Weibull is. But the key is I want you to learn. Okay, just you do what I call the McFadden trick, which is assume all the error terms are distributed Weibull, and then it gets you the probability of picking a certain item, say the item 1, you get these nice probability terms that look like this, not those crazy complicated things even when you assume the error term is uniform. Okay, same thing if you distribute it as normal, you're also going to get a really complicated solution. So remember, assume Weibull. Okay, what am I going to do now? Okay, probability J wins. Okay. Here's what I'm going to do now. Okay. Okay, so now I said the recipe for creating a likelihood function, you pick your dependent variable. Your dependent variable is going to be, first, dependent variable 1 says consumer 1, which mode of transportation does he or she choose? Okay, here's what the loss is by those modes of transportation. Mode I, it equals this term. By the way, we're going to call it loss. Now, I just gave you that case where instead you maximize your utility. Here you're minimizing loss. If instead you just put a negative sign in front of everything, then all of a sudden it makes sense to call this utility, and minimizing total loss is the same thing as maximizing utility, where utility is just the negative of that total loss. Okay, so that's what I'm going to do now. And it turns out, I guess what you'd need to do is whatever estimates you get for A, theta, theta 1, theta 2, you'd have to take the negative of it. The other thing, I think, so you have a negative here. So the key is I'm going to assume that the error term is distributed Weibull. I guess what I'm going to assume, so that Weibull actually is not symmetric. It's pretty close with it. But so instead, what I'm going to assume is the negative of that error term is distributed standard Weibull. Okay, so that's what we're going to do. We're going to wave our hand, say assume theta 4 times ki is or negative of that is distributed standard Weibull. And what that does, we're going to get the probability that given all that. By the way, so I haven't proved that. So, I said if you assume all the error terms are distributed standard Weibull, then you get those nice probability terms. I haven't proven it. I'm sure that there's got to be a few dozen textbooks that prove that. If you want to see a proof, it turns out a later paper that we are going to use in our course. It's the paper by Kurt Signorino. It's a paper that was published in the American Political Science Review. I think this is like mid-90s. And he has an appendix in there and he's going to do the same thing. Kurt Signorino is going to say, here's these choices that it turns out this is a international relations choice, and it's like all these countries have a choice to go to war or not go to war, and their unseen utility of all these choices. Kurt says, let's assume that it's distributed standard Weibull, although I think he's a little younger than I am. I think he said, let's assume type 1 extreme value. And then in the appendix to that paper, he does a proof to show why you get those nice probability terms when you assume that the error term is distributed Weibull. Now, that's crazy that APSR would allow that many pages for that proof, because it's been proven before. It's in textbooks, and I still don't understand why APSR would waste that many pages. Instead, you just should have had a footnote and say, see this textbook. But regardless, so that means for our class, you can, if you want to see the proof, it's in that Signorino paper, and he has a pretty good, I think, a pretty accessible, a little bit of math, but it's math that it's in a poli-sci journal, so it's not overly difficult. Okay, now given that, assume all the error terms in the McFadden paper, that is the theta 4 times ki. Actually, there's a superscript j, because if we're talking about consumer j, the error terms are distributed standard Weibull, then the probability, so I'm going to just pick a generic consumer j, probability j chooses mode I. Mode I is a form of transportation, BART, car, bus, so on, equals, okay, what we're going to do, so we're going to do the McFadden trick, and what we're going to do is take E to the seen utility. That's these terms. The last term is the unseen utility, that theta 4. So we're going to take everything except for that error term. You know what? I'll put it over here so I can copy, and it's going to equal E to that term. And you know what? It actually probably has negative signs on it, but I'm going to ignore those. If on a test or something, that would be fine. I would say, who cares? equals A plus theta 1 CI divided by PF. By the way, and these two terms should have a superscript J. I'll go ahead and put it now. You know what? I'll come back. I'm going to come back and use a different color. So for now, I'm not going to put the superscripts. Okay. So probability, person J chooses mode I equals that plus theta 2 times PW divided by PF times TVI. Darn. And you know what? I'm not going to have enough room on this board. You know what? I'm going to start over. I'm sorry. I should have, what they call pre-boarded. I'm going to use another board. Just so I can write this all out. Sorry, I'm wasting a little bit of time. Okay. The probability J chooses mode I equals E to the A plus theta 1 CI divided by PF plus theta 2 not C, PW divided by PF T the I plus theta 3 PW divided by PF T A I. Okay. Now, that former term had the former equation had an extra term plus theta 4 Ki. So remember, we're talking about a probability, and the probability is a function of constants and parameters and data. It's not a function of a random variable. Okay, so we would leave out the random variable. You would not put that in this equation. Okay, so it's that divided by the sum of so-called J. So let's let K equals 1 to, and let's call it capital I. Or you know what, we could go back to N. Let's call it N. There's N modes of transportation, and I think in the actual surveys that McFadden ran, there was something like 6. Car, BART, cab, bike, bus. Okay. K equals 1 to N, E to the A plus theta 1, theta 1's parameter, CK. Okay, so that's the fare, the bus fare, or the fare, cab fare, bus fare, whatever, the fare we're taking mode K divided by PF. So we're going to sum it over all of them. One of these K's will be I, okay, plus theta 2 PW PF TVK plus theta 3 PW PF TAK. Okay, and now I would say, so this is for the probability person J. Okay, so let's make a superscript J for all these variables. Remember the PW, PF, TVI, all those are data. J, no, we don't have it on the parameter. J. Okay, so that's it. So you'd allow J equal 1 to however many observations you have, how many surveys you'd have. Okay, I equals 1 to however many possible modes of transportation you have. And so for each observation, our dependent variable is what mode of transportation consumer J chooses. Okay, we have that. That's our dependent variable. We would insert these probability terms, pick I according to which mode of transportation consumer J picked. We'd have a series of these probability terms just multiplying by each other. That's our likelihood function. Once you get that, you maximize it, use some tricks. So it turns out that this is called, I can't remember, conditional logit or multinomial logit. Nowadays, you can have R or stata or anything you want, estimate it using that technique, M logit or L logit or C logit or M logit. McFadden didn't have that. McFadden had to program his own Fortran program to maximize this likelihood function. Okay, that is okay. So that's the paper. That's the McFadden paper. I will end there. Okay. That was so this ends lecture 4.7. I'm going to do lecture 4.8. All I'm going to do is talk maybe 20 minutes about the paper that we'll discuss in session 5. That's the Crable Rivers paper. Okay, so see you there in lecture, which will be lecture 4.8.